Okay, so we should be recording. So now I'll try to remember, share my screen. Share. Okay, can you see? You should be able to see my screen now. But one thing, you see the little Zoom window. Now I'm speaking, but it shows you. I was wondering if there's some way I want it to show me when I'm speaking.
I can see you.
You see me, but I see you. I want to see me. I don't know how to do that. Change, make host, rename. Maybe you can show me here. Remove report. See, it shows you, which is okay. If you start speaking and it switches, it's okay. But I wonder if there's some way.
Sorry.
Maybe more.
Please select grid, let's see.
Grid. It's okay, but it's kind of too big.
It's a big one. Maybe.
This one. This one. Maybe I'll just go with this. Yeah, we don't really need to see any. Okay. So, last time, if you can go back and open number 3, train, and I was having trouble with the print statement. Okay, so I want to change this. So now it says epochs 100. Make it epochs 1. Okay, and then a go. Hopefully it will print. Accuracy, right. Okay, but let's say that we want, you remember we had this underbar here, means ignore the, so it's called a loss. So for example, if we wanted to say loss, so the thing is for print, you see this, there's a string and then a % sign. Okay, and then there's a brackets. The thing is, I mistook. It has to be inside the brackets like this: loss, comma, accuracy. Okay, I'm used to C, so you can do something like this. F. Okay, now if you run this, it should work in theory. Yeah, here's the losses 5.1 and accuracy. Okay, so this is one way to do it. There's actually 3 ways to do a print like this in a Python. So if you search like if you do like Google Python print, I can put this in the chat actually. Chat, where is chat? Let's see, I have to stop share. Then I can chat. Chat. Okay, so now you should be able to close. And then I'll share again. Okay, there's actually 3 ways to print with a format. Okay. So print. 3 ways. There's print F style with a % and the format and an F string. Okay. So for example, this is the print F style, which I'm used to. If you're used to programming in C, then this makes sense to you. However, if you're not used to C, then maybe printf style, right? So the percent sign here, it joins string with a variable like this. Okay, so this is different from C. In C, you just have to put in commas. You don't need the percent sign there. So strange, looks strange for C programmers. The second way is with this format. So for example, we could have done like this. If you go back to Spider, you can do a dot format. It's a big F format. Format. And then I don't need the percent sign like this, maybe. Doesn't look right. Let's see. Small f format. All right. Then I replace, instead of percent signs, you replace these with brackets like this. Oops. Oops. This. So in theory, this should work. Let's see. Look the same.
How do you specify the decimal into?
I don't know. You have to read further. Don't ask me, I'm not a Python programmer. Okay. I think it's automatic, it just automatically computes I don't know how to do it. And it doesn't say on this homepage. There is one more way with this, they call an F string. Maybe, I'm not sure. Curly brackets. Maybe with X's you can do it, I don't know. It's homework assignment. So the third way is with an F string, they call F strings. F strings. Okay, so if we wanted to do this with an F string, we would say print. All right, so then, okay, so we would put an F here. F, is that right? And then we don't need the format. So you could just do loss. Oops, what did I do? Loss. Cut all this. I should have copied these. Put inside the brackets. Maybe like this. Unmatched. Too many. Okay. Let's see if this works. Okay. The three ways. Your assignment is to figure out how to specify the number of digits. Okay. Okay, so let's what else? So there's a couple kind of yesterday, just kind of review what we talked about on Monday. Let's see here. So tips for reducing overfitting. So these are just general tips. So if you remember, overfitting means that it's training very well on the training data. Okay, it may get 100% correct on training data, but when you try to test it with some new data it's never seen before, it does poorly. Okay, that's called an overfitting. So the first method is a dropout. So usually between 20 and 50%. Okay, too high. Yeah, if you do it too high, then you'll get what's called underlearning. Means it won't, the accuracy will not go up. It'll just stay flat. So you don't want to overdo it. But dropout is very easy, simple way to reduce overfitting. And you can use it on the hidden layers. The first layer is the input is the input layer. Okay, and hidden layers, you can use dropout on both layers. Okay, another method is to use a larger network. So we saw last time you can add a layer. So we started off with just one hidden layer. You can make it 2 hidden layers or 3 hidden layers. You can try. You also make it wider. You can add more neurons to your network. And we haven't talked about learning rate yet, but you can try the learning rate. Usually you start off with the default. The default is usually a 0.01, I think, and try to multiply it by 10 or 100 and see if that helps. Okay, size of network weights, and this last one is sometimes if you print out all the weight variables, you'll see sometimes they get very large. Okay, that's called what they call exploding gradients or something. I forget. Anyway, you can try this normalization. I think later we'll have an example. Okay, but that's kind of a last resort. Okay, ways to lift your performance. Tips for using learning rate schedules. Increase initial learning rate. Okay, we've been using this Adam optimizer. Okay, I think the A, I'm not sure, but I think the A of Adam stands for adaptive, means that the learning rate will change accordingly. So normally you don't have to worry about the learning rate. But there's another one we'll see later. It's called SGD, stochastic gradient descent. It's a different option besides Adam. And in that, for SGD, you normally specify the learning rate. So sometimes try it like times 10. If it improves, then try multiply by 100. If it improves, keep doing a multiples of 10 like that. Okay. And momentum means how much it changes while it's training. So you can change the momentum variable and different schedules. So this gets very detailed, but playing around with the learning rate sometimes can help to speed up the training. Okay. Okay, so this is papers with code. So when you're doing a research, sometimes you find a good paper, interesting paper. Okay, but it's almost impossible to create a working Python program that implements this method in this paper. So this website is called Papers with Code. Okay, so this has a papers and code that you can start off with. Okay, so this is, for example, if super resolution is something we'll talk about later. Let's say you are interested in this topic, super resolution. So just type in super resolution, and it'll take you here. And then scroll down, and you'll see the papers, different papers related to super resolution. Okay, so so for example, if this looks interesting, first click the paper, download the paper. Okay, so something like this. A lot of these papers are from ArchiveX. Archive. So these are not peer reviewed. Okay, so they're if you're some people they kind of look down on archive, but it's good because if you have a new idea and you want to get credit for if you submit to say Nature, okay, it may take 6 months for the review process, right? So in that time, somebody else might publish your same idea. So ArchiveX is a way to get your idea, say this, I had this idea, so I get credit. Okay, so usually people they submit to ArchiveX first, and then they submit to Nature or Science or one of the big high impact factor. But the other good thing about Archive is that it's totally free. So if you're not in a university, it's difficult you have to pay a subscription fee to major journals. Okay, so yeah. So that's a good thing about ArchiveX. And actually there are other Archive is not the only there's another one. I think Nature has their own kind of archive-like system. You can submit papers. Okay, so anyway, so go back to here and press on this code button, and it will take you here. Okay, so the code, you see there's for this one paper, there's 51 implementations. So 51 people around the world have developed the code, and they're ranked. Okay, so you see on the right over here, there's a PyTorch and TensorFlow. Okay, so you have to, first thing you have to decide, do I want to work in PyTorch or TensorFlow? Okay. So I think I'm not going to, I don't have much experience with PyTorch, but PyTorch is basically a Facebook. Okay, so TensorFlow is Google. Okay, so what do you like? Do you like Facebook or Google? You can choose. I tried to find a good comparison between PyTorch and TensorFlow, but I wasn't able to find it. I don't know which is better. Some people, it seems to be about 50-50. So whatever, you can try them both. And above you see it says Torch. I think that's an older version of PyTorch. Okay, and the ranking, what I found about these rankings is that usually the highest ranking is the oldest code. So it's not necessarily the best. So I would recommend that don't necessarily use the highest ranking here, but try to download some, as many as you can and find one that, actually works. Okay. Which doesn't, lots of times. And the other thing, lots of times the code is old. So that's where I was saying Anaconda is good, because if it uses Python 2, you could be like me and try to update everything to Python 3, right? But it's a lot of editing. You have to change things, and some things are not so easy. Most things are easy to update to the latest version, but not everything is possible. So sometimes you have to go back to an older version. So that's where Anaconda is good, because you can select, when you create a new environment in Anaconda, you can select Python 2 and go back. Okay, this was just a general about AI. So one thing about AI is people think that the robots are going to take over the world. But personally, I'm not convinced. So the one thing that AI is not good at is predicting the weather. So you think about the weather forecast is good for about 10 days. After about 10 days, it doesn't matter. You have a supercomputer and you have terabytes of data. It still does not improve. Another thing is stock market. If you can plug in, many years of stock market data into, and you can train an AI. That's what we said, a regression. Okay, you want to predict what will be the price of the stock tomorrow. Okay, if you could do that, you would be a very rich man. But it's not so easy. That's the thing about AI it's not magic. Okay, it's statistics, it's mathematics, and there's certain limitations. Some things it's good at, but some things it's not good at. Okay, especially with weather, they say the most difficult weather, they say, is local and severe. So for example, tornadoes are the most difficult. Hurricanes are very large, right? So they can say, well, a tornado or a hurricane is coming, so you have several days to prepare. But tornadoes are very local. So tornadoes are the most difficult thing to predict. And this, I think we'll do later. Anaconda. Yeah, I thought I'd take a minute just with Anaconda, look at some of the other options you have here. Data spell, I have no idea what this is. I've never used it. Command is just will launch a command here. So usually you change direct. This is just on Windows. It's just like what do you call it, command line. And then Python. Usually you do Python, and then the name is something that Python. And I found that I use this when I'm using the GPU. For some reason, in my environment, in my computer downstairs, I can't get Spider to work with the GPU. Don't ask me why, but I was able to do it with command line. So sometimes this is useful. So command line. Now Jupyter is very popular, but I've never been able to quite figure it out. Okay, if I would recommend that you try Jupyter, because especially amongst young people, I feel like an old dog cannot learn a new trick. Okay, so I say go for it, but not for me. And Qt is another console here. I don't know what the advantage. Launch Qt console. This is maybe more like a Linux. Yeah, I haven't tried. Yeah, this is more like a normal console, like in in Spider here. You have a console here. You can enter commands here. Right? Whatever. Okay. The Qt Spider. Data Laura, I don't know what this. IBM Watson. This is an interesting story. If you go on YouTube and Google for Watson, and in America there's this game show called a Jeopardy. So if you Google Jupyter, why don't we just do it? Jeopardy. Go to Google. This is actually an interesting story. They made this computer robot to compete in this game. The Jeopardy, all right? Jeopardy and Watson, maybe. Jeopardy. Yeah, if you're interested, you can watch this video. So they made this AI. They trained it on all of Wikipedia, and but it has to go in real time because they're competing with in real time with humans, right? So a lot of things are actually pretty easy for the computer. For example, who starred in this hit movie, right? It's actually pretty, and the computer can get it instantly, right? But some questions, they're worded, they're kind of tricky the way the questions are worded. So pretty amazing they are able to compete with these people are very famous. We call it trivia. They know like who starred in this movie and who's the president of this country and all these trivia questions. Okay, so that's what Watson. See this IBM Watson. And they tried to, after they finished with Jeopardy, they tried to use it for a hospital, kind of like Chat GPT for hospitals. But apparently it was never really caught on. And think about AI. AI gets a lot of hype, right? But it doesn't always, deliver into real results. So anyway, it's an interesting story. Oracle Cloud, I have no idea. I never tried to use this. Console, Mini Conda, I don't know. GlueViz, I don't know. Feel free to try out. You can just install, or you can, our studio, I think, is for statistics. Our PyCharm Professional, I have no idea what this is. Another IDE. Okay. What are we doing here? We got this one. Okay, I think this is another website. Today we're going to be talking about numbers. So this is another good site. If you're interested in the theory how neural networks actually train, because he developed this handwritten it classifies handwritten images, but he didn't use any Keras or PyTorch. It's all in Python. So it's if you're curious, it's a lot of reading, but he really goes in a lot of good detail. I recommend if you want to go back, I understand, especially this gradient descent. How does this great gradient descent you hear a lot about? Normally with Keras, you just it's like a black box. You just give it your data and pray that it works correctly. Okay, what about this one? All right, so these are other good sites. If you want to learn more about theory of AI, this is on YouTube, this course from MIT. There's a good one here from MIT, and there's another good one here from Stanford. Okay, so MIT and Stanford are kind of the leaders in this field. So what I like to do is before I go to sleep, I like to click on the lecture, and then I fall asleep very soon. But it's good when you have time to listen. So talking about GPUs, my computer in the hospital is like this, so it's pretty decent. But if you have a budget, if your boss says, "Oh, we have $100,000 we need to spend," then tell them I want this. This has 4 GPUs in it. So sometimes they have 2. A normal computer will have one GPU. My boss just bought one that has 2 GPUs, and this one has 4. But you would think that it has 4 GPUs, it would run 4 times faster. But I measured, between my computer and this computer, and it was about twice as fast. Okay, so, but the other thing is a RAM. So this is RAM on the CPU RAM, but there's another GPU RAM. So I have 8 gigabytes on my GPU, but this one has 24 gigabytes. So especially if you're doing high resolution, like if you want to do super resolution with, say, a 1K, you want to blow up an image from 256 to 1000, then you need a lot of RAM. Okay, it doesn't matter how fast it's, of course, faster is better, but if you don't have enough RAM, then you can't, it won't run at all. Okay, that's GPUs. And also there are web services. For example, Amazon has a web service. If you the problem with buying a computer like this is that after a year or two, it's already obsolete. So it may make more sense to subscribe to a web service like Amazon. And also the university, at Hokkaido University, they have a computation center. So you have to apply to get an account, and then when you run your program, you have to submit it as a batch. Okay, so it's a little more inconvenient, but then you have a real supercomputer. So if you want to train on really big, lots of data, then I would recommend something like that. Okay, CFAR, we'll talk about this a little bit later, I think. This is just a database of images. Okay. So the next topic is numbers. Okay. Okay, so handwritten. Okay, so in Japan, they have this concept. In America, we have Christmas cards. We send at Christmas, we send cards to our family and friends. In Japan, they're called a nengajo. It's a New Year's greetings cards. So in Japan, they get really crazy. They want to send a card to everyone they know, not just their family members, right? So people literally will write hundreds of these cards. And so you can imagine, and the tradition is for the cards to be delivered on New Year's Day, right? So that makes a huge job for the post office. You can imagine they have millions of these cards they have to deliver on one day. But you see at the top here, it's the postal code. In America, we call it a zip code. In Japan, we call it a postal code, right? So you can imagine it takes a long time to sort through all these millions of cards like this. But nowadays they have they call a sorter. They feed them into the machine, and the AI robot will look at this postal code and put them into different bins. Okay, so this one has been printed on a computer, but even if you print it on a computer, different computers have different fonts, or they have slightly different, darkness of the ink, right? So there's a lot of variation in the way it's written. So it would be nice if we could automate this process, right? So this MNIST database, NIST, NIST is National Institute for Science and Technology. I think in America, it's the branch of government that, for example, all the clocks, how clocks are synchronized, and they do all kinds of how weight, when 1 kilogram is going to be this. And an M is a stands for modified. So this was I think Cornell. This is Cornell, I believe. Yeah, they took this data from NIST and they modified it, and you can download it directly, but you don't have to download it because it's built into Keras. This is kind of like the hello world for AI. So all students, this is the first project they are assigned. Okay. So anyway, they have all and at NIST, they got the volunteers to write digits from 0 to 9. Okay. And some people, have very nice handwriting. Some people not so easy. Okay. So the first step is to plot the data. So if we go back to Spider here and we go back to numbers. Number 1 is plot. We can close this one. So hopefully, if you run this, it will work. Pray. Okay. Is it working for you? Okay. So you can see up here at the beginning, from TensorFlow Keras import data set MNIST. Okay, later we'll see other data sets. These are sample data that you can use to study. And okay. So all it does, this has, you can see here, it loaded 60,000 training and 10,000 testing. Okay. And each image is 28 by 28 pixels. Okay, and the Y, you see over here, Y. So if you go back to variable, you should be able to, X is X. Okay, this is let's see here. X is the images, okay. I think. Let me wonder if there's no way to clear this rate of float. Maybe I should oh, I see. Set a breakpoint here and then debug. Okay, then step over. Okay. So now test X, you see, our train X is 60,000 images that are 28 by 28. Okay, if we can't, it's too big, so don't try to open it. Test X is only 10,000. That's too big too, okay. But the Y, I wanted to show you, is a Y for training 60,000 of these. Okay, so this means that the first image is a 5, supposedly. So we look at our plot here, we see, okay, the first one is a 5, The second one is a 0. The next one is a 4. So you see the Y is a label, and it's correct. Okay. Okay, and then we just go in the loop and we plot the first 9. One thing I wanted to say, this plot 330 plus 1 plus I, what in the world is that? I could never figure that out. I think if you go to if you Google and then next word, what's this? You bet. Quit. Subplot. Okay. Subplot. Boom. Okay. So actually, I prefer this style. This is one style, but it's let's see. Let's make a copy of this, and then comment this one out. I don't like this style. I prefer like this: 3, 3, and then I think this is the same thing. Okay, this means rows, columns, and an index. All right, rows, column, index. So I think this will do the same thing here. Let's stop this. Run. Did it work? Yeah. Okay. So these two are equivalent. So this is one style of 333 just means 3. 330 means 3 3 rows and 3 columns. But what if you have more than 9 columns? I don't know how to do it with this style. So I like to break it up like this. Okay. So next, what are we doing here? 9:30. Right. So this is we used this one MNIST down here. Okay. But there's other ones. Before we saw this Boston housing. Remember for regression, we had the CSV for this. Okay, but you can also get it directly from Keras data sets here. And a CFAR 10, I showed you the image before, the sample images. So 10 means that there are 10 categories. So it's like boats and cars and horses. But there's another one, CFAR 100, because that has 100 categories. Okay, so if you have a powerful GPU, you may want to try playing around with CFAR 100. And fashion is similar to handwritten digits, but instead of numbers, they're pictures of like jackets and shoes. Okay. Then these IMDb and Reuters are used for training text. Okay, so later we'll see an example how to use those. Okay, so those are data sets. Okay, so we did this. We loaded 28 by 28 pixels, and it's a single color channel, right? Right. Okay, so this is the next step here. So let's go back to Spider and open number 2, train here. Okay. So this gets more complicated soon. So you put a breakpoint at the first line here and debug. Okay, it loads everything. Okay, then a step into test here. Okay, step over. Okay, so first one, step into load the data set. Okay, the first thing it's saying is we load the MNIST data, and then we print, same as last time. We have 60,000 training and 10,000 for testing. So this next line, because we're working on a notebook computer, okay, if we used all the data, it would take hours and hours, right? So what we do is we want to use 1/100th of the actual data, okay, just for because we're doing this live in class, okay? So factor, when you're ready to run on a GPU, set this to a 1, and that will use all 60,000 data, okay? But for now, we have a reduction factor of 100, 1/100th. Okay, so this next line, if you go back to train, or you go back to your variables, okay, so train X is train, not test, train. Train is 60,000, 28 by 28. Okay, but we want to resize this. If you watch the 60,000 here should go to 600, right? This, did you see that? Changed, reduced the data from 60,000 to 600. Okay, same way with test Y. Where's test Y? Here, train Y, excuse me. Test, I got test and train. Okay, so test X, we have 10,000. Okay, we're going to divide that by 100, which is 100, right? Okay, same way with the Y. Remember, Y is the labels, right? So Y is going to go from 10,000 or 60,000 to 600, and this will go to 100. Okay, so now we have 600 input data, training data, and 100 testing data, because all we did is divide by a factor of 100. So we use this NumPy resize function to do that. Okay, so next we'll print out reduced data is 600 and 100. Okay, makes sense? So that's one thing, it's a good skill, is to start off with a limited amount of data. Don't try to use all your data, because it will take hours and hours to train. And you might have a simple bug at the last step. You know, you forget to save your model at the end, and then you have to start all over. So always start off with a limited amount of data. So next, we're going to reshape. Before we use resize, okay, which is NumPy, but reshape is part of Python. We can this works directly on the array. We have a train X now. So if you watch train X, now it says a 128, 28. Train, excuse me, train X here, 628, 28. So if we step, you see it changed, added this 1 over here. Now it's 628, 28, 1. So the 1 means that it's a grayscale. Okay, later we'll look at color images. So this will be a 3 here in the last. Okay, but when we are training a grayscale, we have to add this 1 over here. Okay, so same way with test X. Test X here, he says 128, 28. If we step, it goes 128, 28, 1. Okay. So now our reshaped data looks like this. Okay, so you can right. So sometimes so for example, test X, if you try to open this, it says it's 4-dimension data it cannot display. Okay, but you can still get some idea of what it is with a print. If you want to check, for example, test X, X, for example, you want the first image. Okay, what does the first image look like? You can do this. Well, okay. So there's 28 by 28. Okay, it's too much data. So let's say we don't want the whole image, just the middle row. So we know it's 28 pixels. So we can do the 14th row, for example. Looks like this. Okay, so this should be 28. This from the left, it's going across. They're all zeros because it's white. And then in the middle, you have these high pixel values, means where the pencil hit the paper. Okay, so you can use the console this way to check make sure your data looks good. Okay. So the next step is a train Y. We're going to use this 2 categorical. Okay, the problem is that train Y looks like this. The first one, remember, was a 5. The next one was a 0. Okay, but remember, we want to use a 1-hot encoding. Okay, so if we step over this, now train Y looks like this. Okay, remember a 5, we're going to put a 1 in the 5 position. Okay, so this is what they call a 1-hot encoding. The way I like to think of it is that I'm 100% certain that this is a 5. Okay, and the next one, I'm 100% certain that this is a 0. Okay, that's the way I like to think about it. Okay, so we do the same for test Y. Okay, so now the train and test, you see this comma 10. Okay, we have 600 training data, comma 10 means that there are 10 categories. We have categories 0 to 9. Okay. Any questions? Simple, Simon? Okay, let's go on. Okay, the next we're going to prep pixels. So let's step into this. Prepare our pixels. Okay, so the first thing. So here again, now we just call it test and train. So here, for example, we can print test, the first one, and the middle row. Okay, so this is normal pixel values. This is normal pixel values are 0 to 255. That's an 8-bit pixel value. But AI, when you're training AI, you don't want to use like this. You want to everything from 0 to 1. Okay, so this first it just converts everything to from, you see now it's int 8, right? So we're going to convert that first of all to float, 32-bit float values. Okay, so now if we print test underbar normalized, oops, no, train, sorry, train. I haven't done test yet. Sorry, I want test. I want train. Oh, sorry, I want train. Not test. Train. Okay. So now they look just the same, but now they have a little decimal point. Okay, we converted from 8-bit integers to 32-bit floating point values. Okay. So to do the same thing with the test. So this next step here, we'll just divide everything by 255. So 255 will get a 1 and normalized, right? So here, if the value is near to 255, it gets a 0.999. Okay, so this is what we want to use for input to our network. Okay, any questions? Hope not. Okay, so we're not worried about the time yet. Okay, so here we're going to step into this, evaluate. Okay. So number of folds is 5. Okay, so this is going to run 5 times. And I want to go through. Remember, we'll do it 5 times so that we have some statistics. So we have an average accuracy rather than normally you just do it 1 time and you just assume that you have a good value. But it's better. Actually, you can specify this function. You can specify 1 down here, number of folds. You specify 1. But anyway, let's. I want to show you the model. Okay, so we loaded the data. 28 by 28 single color. 10 classes, 1 hot encoding, 2 categorical. Okay, so we covered that. We prepared our pixels, range 0 to 1, right? So it started off like this, and now it looks like that, right? That works. The next thing is the model here, okay? So before, I haven't really talked about before we just used this dense here. Okay. So dense is another word for a fully connected layer. It means all the neurons in this layer, they're all connected to all the neurons in the next layer. Okay, I'll show a image of that. But now we're going at the top, we have this convolution 2D. Okay, and in between we have this flatten. Okay, so in these kind of image classification networks, you always see the same pattern. At the top up here, they call a feature extraction front end. comprised of convolution and pooling layers. Now, I'll explain what this pooling is later, but always you see the same pattern. Up here you have convolution, and usually you have more than one of these layers. Okay, that's why they call it deep learning. Okay, as you add more and more layers, it gets deeper and deeper. That's why the word deep, you hear that a lot. But at the bottom, it has this classifier. Okay, you see the dense here. That's another name, like I said, for fully connected layer. So anytime you want to classify data, you use this dense. You say this is here. Okay, and they're connected by this flatten. Okay, so now we have a 28 by 28 image, right? But before we send it to the dense layer, we take all the columns, rows, put everything on one long line or one long column, however you want to think about it. Okay, so flatten just takes a 2 by 2 image and makes it one long one-dimensional image. Okay, so you see this pattern over and over again. Okay, so what is a convolution? So if you've ever done image processing, you're familiar with this idea of a filter. And this is the input pixels, and these values here are called the kernel. Okay, so this is maybe like a sharpening. It might be a sharpening filter or a edge detection filter. There are several of these kind of filters. But the idea for AI is that these values inside this kernel start off at random. Okay, and it uses the kernel first. It's just random numbers, so it doesn't know if this is, for example, classifying zeros and ones or twos. It gets the wrong answer at first, most of the time. But it's called a back propagation. It updates these values in this kernel here. Okay, so that's what you're training. This is what is being trained when you run the fit to train your data, train your network on your data. Okay, so that's why you hear this word a CNN, convolution neural network. Okay, this is what a convolution is. It's just a filter, image processing filter. Okay. So another word you see a lot is a stride. So normally we apply the filter, if it's a 3 by 3 filter, for example, this red square, the output will go in a single value. It will reduce this 3 by 3 pixels into one pixel here. So normally we stride of 1, we'd go to the adjacent pixel. But sometimes you see stride of 2. So instead of going to the adjacent, it'll skip 1 pixel. Okay, so stride of 2, stride of 1, these are what I was saying yesterday, hyperparameters. Okay, the advantage of using stride 2 is that it reduces the data and it'll speed up training. Okay, sometimes if it's use stride of 1, it takes too long to train. Okay. And padding, sometimes you want to see the output, if you use stride of 2, especially, the output is much smaller. Sometimes you want to keep this image the same size. So you pad the margins. Okay, so that will keep the output the same size. Sometimes you see this padding. Another one, a pooling. Okay, so what does pooling mean? So it's very simple. For example, usually it's called a max pooling. So max pooling just this two by two block. Just find the max value within this block, and that is the output. Okay, so very simple. GPUs like very, very simple algorithms. Okay, they don't like GPUs don't like complicated mathematical functions. Okay, that's why you see a lot of these, yesterday we said ReLU. ReLU is a very, very simple algorithm. Max pooling is a very, very simple algorithm. Okay, you see this a lot. Okay, so feed forward. So this is a network here. By the way, I got this image from, I showed you earlier from this page here. So if you're interested, if you're interested in how this classification works, okay, you can read this. But okay, so this in this image, it shows the network. You notice over in between here and here is a convolution, and then the flatten. But that doesn't show that in this image. We're only worried about classification layer here. Okay, so feed forward means that you take each pixel value, and you see this this column here. It only shows a few neurons here, but this actually has 784. So this column is actually very tall here. It won't fit on the screen. Right, so 28 times 28 is 784. So we feed this into, this is called the input layer. And then here we have one hidden layer with 15 neurons. Okay, so this is what I was saying, a fully connected layer, also known as a dense layer. Okay, so the output, there's 10 outputs. Okay, so think of each one as a probability or confidence level. How confident am I about the result here? So for example, the prediction might look something like this. Okay, so I'm 70% confident that this is a 5, right? However, when you start off training, maybe you get the wrong result. Okay, right, so this is the label, that this is the one hot encoded label. Okay, so definitely 100% this is a 5. Okay, so what you do in back propagation is you multiply everything backwards, and update all the neurons in this hidden layer. Okay, so if you guessed right, then it doesn't have to update anything. But usually when you start off, you guess the wrong number. So you have to update these neurons here. Okay, so we have a feed forward back propagation, and you go back and forth, back and forth, back and forth, back and forth, many times. Okay, so that's why you need a GPU can do this in parallel, can take this whole 10 vectors here and multiply it in parallel. Okay, so it's just as fast if you have one value, or if you have 10, or if you have 15 here, it does it in parallel. So GPUs are good at doing very simple operations in parallel. Okay, so back prop, feed forward. So right, so this is why I'm saying the structure for image classification is often have these convolution plus pooling layers. Okay, then you have a flatten, which will input. So the height of this is the same as the width times the height of the input. Okay, So it shows it like this, but it's actually probably much much taller than is showed on this diagram. And this is a fully connected layer or layers. Usually you have more than one layer. Okay, so this is where the classification the convolution layer, think of it like edge detection, finding out where like the beak of this bird is a sharp edge. Okay, so that's where the edge detection happens. And then we flatten it to the fully connected layers. And then the output, we use this called a softmax. Okay, so if we're confident that this is a bird, then it will have the highest value will be here. Okay, so the CNN, convolution neural network. The convolution, remember, comes from this. And pooling is to reduce the amount of data. If we use no pooling, it would take too long to train. And pooling also, it kind of gives a kind of a summary. A low resolution version of the image gives kind of the general shape, not too much detail. And then we have a fully connected layer, also known as a dense layer. Okay, so I wanted to show you this. This is kind of cool. This is from Stanford. And we'll go to Zoom. I have to stop sharing. And then chat. Okay. We should also put that to share. Yeah. Okay, so if I go to here, you have to wait a second for it to start. Okay, this is really cool. This is, I was saying before, the CFAR images. Okay, so on the left over here is the input image. And then you have all these convolution layers, which think of them as kind of like edge detection. Okay, in the middle here is kind of a graphical representation of the convolution layers. And then the final layer here is the softmax. Okay, so on the right here, it shows the top 5 results, but they're actually 10. This is CFAR 10 data. So there are 10 categories. There's frogs, there's deer, cats, airplanes, and so on. Okay, so it's kind of cool that and the thing I wanted to say about this was that when you're using the neural network like this, it's very fast. Okay, the thing that you need a powerful GPU is to train your data. Okay. 10. Okay, we have 15 more minutes. So even if you just have a phone, okay, the phone does not have a powerful GPU, right? But you can still run a neural network like this on your phone, no problem. So to me, it's amazing. You'll notice that it's not 100%. Here's a bird, okay, a dog, okay. If you watch it, it'll make a mistake. Dog, bird. See, it said bird. You can catch it, make a mistake. Okay, so it's not 100%, but that is AI for you. Okay, so let's go back. Oh, this is the next topic. I don't want to talk about this. So let's go back. Okay, so we defined our model now. The next step, where are we? Okay. Select rows, test and train. I forgot what this is doing. Train oh yeah. This is just so that we're divided up into five pieces. We have we run this 5 times, but let's not worry about that now. Let's reduce the data. We talked about this. Okay, I'll have to come back. This. Okay, let's try this. Let's you see at the bottom of this train test. Okay, this number of folds, let's set this to 1. Now it's 5, but we don't have all the time in the world. And then press run, not debug. Okay, hopefully it'll start. I'm going to do 10 epochs here. Okay, so you can see at the beginning, if you go back, after the first epoch, the accuracy is only a little over 50, 54, 55%. Okay, which is actually, remember this is numbers now. Okay, so really, if this is kind of interesting. If we set this batch size to 1, so this is, yeah. So let's set this batch size to 1 here. Let's see, now it's 32, remember. Okay, we're gonna go 10 epochs. Okay, so this, you'll see it should start off, accuracy should start off as 0.1. It still does pretty good. Starts right off at 0.6. Okay. Anyway. So even after the first epoch, it's still training with 600 images. Okay, the accuracy is already pretty high, higher than I would expect. You would expect that it start off as a 10%. Okay, but actually did it even better. And by the end, it's up to 100%. So not bad. Okay, and so the plots we will ignore for now. But if we were to run this, where am I? Where am I? Here we are. Okay. We did this, reduce the data. Okay. So if I ran this on my GPU downstairs, so here, now we have 600 data. So that if you run this 5 times, you'll get a result, something like this. Okay. But if you run on the full data, so if the reduction factor is 1, means 100%, then we get up to like 98%. Okay, and you see the statistics here. If we're only using 600, you see there's a standard deviation in our result here. But if we use all 60,000, we have better statistics. Okay, but we don't have time in this class to do this. Okay, so CPU. So normally when you're training, you'll see the CPU will go up to nearly 100%. Okay, but if you have your GPU set up correctly, then you'll see it usually doesn't go up to 100%. Usually the GPU might only go up 10% or 30%. Okay, the reason for that is that there's a lot of overhead to using the GPU. You have to send data from the CPU to the GPU, and you have to send the result back. Okay, so in a perfect world, the GPU would be utilized 100%. Okay, but rarely do you see that happen. And in special cases, if you get into CUDA programming, you can program the GPU directly. But normally we use that's what TensorFlow is doing for us, so that we don't have to worry. So the good thing about TensorFlow and a Keras is that we can run on a notebook computer like this with no GPU, or we can take the same code and run it on a supercomputer, and we don't have to modify our code at all. We just let TensorFlow figure out how to parallelize on the GPU. Okay. So, okay, we have about 5 more minutes. What else do we have here? Visualize it. Okay. So the easiest way is just to print. So when you, here is our model here, and we print. Okay, so we can see there's this input is, why is it 26? Should be 28, I'm not sure. Something strange. Input shape is 28, right? So the input is 28 by 28, but we have this convolution which will reduce the size by 2 pixels. And the next step is max pooling. So we're going to do 2 by 2 max pooling. So that will reduce the size by more, down to 13 by 13 pixels. Okay, so then we go to the flatten. So this 5408, I think if you multiply 13 by 13 times 32, maybe, I'm not sure, should come up with 5408. Okay, so we have a one hidden layer here with 100 neurons. And then the output is 10 because we have 10 categories, 0 to 9. Okay, so another way is we can make a plot like this using this plot model here. Okay, so these are very easy ways to visualize your network. Okay, so we have a base model, but maybe we can do better. So one way is to increase the model depths. So now we have 3 of these convolution 2D layers. Okay, so this is kind of the arch of defining your model. There's no good rules, but there are guidelines. There are no rules, there are only guidelines. So for example, try to double the number of layers and see if that helps. So here, we went to accuracy. Accuracy it's already 99%. Okay, so here it's a deep model. Okay, and I talked a little bit about this last time, but when we do the final testing, we want to use all our data. So we don't want to we want to use all the data that we have for training. Okay, so that's why we use the what was it called? It was called what was it? A number of folds here, right? So when we're trying to figure out if it's working, we set this to 5. Okay, but when we're confident, okay, we're not going to, this is the best model that we can possibly, then we do it folds as one, means you use all your data for training. Okay. And then we save the model we talked about last time. Save your model. Okay, so then we can try to evaluate. Okay, so for example, if we open up number 3 here. So this will right, so this we can just run this and it will just I think if it works, let's see here. Oh yeah. Okay, this is what this is doing. You can stop this if you're running. This goes into a loop, and with all the training data, it tries to find misses. Remember, it had like 99% accuracy. Okay, but what about the 1%? So if you let this run, it takes it a long time. But if you go, you see this miss folder here. If you go inside of here, you can see the ones that it missed. So for example, this one, very small. Remember, this is just a 28 by 28 image. Zoom. Okay. Okay, so this 62 here, this means this is the index. We have 60,000, but this was index number 62. And it guessed that this was a 5, but the actual result was a 9. I should have guessed 9. Okay, so it's a good idea whenever you are doing this kind of classification, is to make a list like this of all the data that it missed, because that might give you a clue. You might see some pattern. In this case, some of them are, I think even a human could not guess. This is supposed to be a 5, right? But I look at it and it just looks like a blob. So that's the thing about this kind of AI, is that sometimes it's impossible. Sometimes the human just wrote something that is totally unrecognizable. Okay. Then okay, so it's 15 minutes now. So let's stop now and